everyone, my name is Riyad and this is the continuation of the Week 2 Machine Learning Fundamentals MLF program by UTMIST. So earlier, during the lecture, we went over all the theoretical aspects of logistical regression and the topics that are building up to that. We went over the mathematical and statistical foundations and what it means in general. So if you haven't watched or if you were not present in the lecture, I would strongly encourage you to go to the slides that are linked on the website of UTMIST and go through all the explanations in order to understand the theoretical concepts. And only after doing that, please come back and watch this video that will be about coding and the practical aspects of logistical regression. But if you were present in the lecture, this is a perfect opportunity for you guys to solidify your skills even further and to work on the coding and understanding what are some of the most important functions and how we can go about, building our own model that's about logistical regression in Python. So without further ado, I want to get started. So I will be working on the IBM platform, the link to which is already shared with you through the Discord chat, as well as it's also linked in the UTMIST website. And the reason I'm doing that is I want to sort of walk you through the same experience that you would have, and that's why I didn't, decide to or choose to do this in VS Code. You basically would be doing exact same thing if you decide to code along with me, which is coming to this platform and making sure that the Python 3 IPY kernel is selected here, just basically going by the chunks of code and running them in order. The first chunk of code that we will be running is this the code block that's about imports and installing and some command lines. This should give you this kind of output with some text, which just means that all the necessary dependencies and all the dependent files are being uploaded, and they must have already been uploaded because the way to confirm it is by seeing this utils.py. If you have this utils.py, when you open this tab here, the file browser, it means this run was successful, and then we can move on. So the first section is from linear to logistic regression. So as you remember from the classification predicts a class label. We start with a linear score, then squash it into a probability using sigmoid function, right? We have our weights vector, we have our input vector, we have plus this scalar bias, and then this gives us z, which is our activation input, and then we use this activation input in the sigmoid function using this formula here, that just gives us the probability. The model is built upon predicting class 1 when the sigmoid of z is greater than or equal to 0.5, and class 0 otherwise when sigmoid of z is less than 0.5. The line where this sigmoid function is equal to 0.5 precisely defines the decision boundary. So let's start with an exercise. We are going to implement sigmoid function ourselves manually. There is a function in the PyTorch library that could perform the exact same function for you, but we're not going to be using that, right? We're going to do it ourselves. This was the function that I was talking about, just torch.sigmoid. But it's going to be fun. So let's go ahead and do it. So the first thing that you want to make sure is that we're going to be using sort of different variation of the same formula depending on the value of the z. If z is greater than or equal to 0, so if it's non-negative, we can safely use this variation of the function that's also depicted here, and then that's also been shared with you in my lecture. But if z is less than 0, so if it's negative, we want to be using this equivalent form of the same formula, and that is because if z is super large negative number, or when I say super large negative number, I mean very negative number, right? Negative something super big. This bit here becomes obviously positive, and then the e number, right? To the power of this very large number becomes also huge, and that causes overflow over zero or overflow over infinity, and zero over infinity, and that just makes our whole function a little bit unstable, doesn't give us stable results. So that's why, to be on the safe side, we're going to be using the same formula in different equivalencies depending on this case. So I hope this bit, like this hint section, is clear for you folks. And if it is, I think we can get started. So first thing that we need to do is to make sure that we clearly sort of separate the positives from negatives in Z, right? And Z is our input here. So I'm gonna define two variables called positive mask and negative mask. So the positive mask, as you would understand, is going to be basically Z as a tensor when it's equal to or greater to 0, right? So when it's non-negative. And negative mask is going to be exact same tensor, except only when it's negative, right? As the values of Z are negative. So I can just flip the positive mask that I defined above. Okay, so this makes sense. And then I also wanted to create a output tensor that's going to be exact copy of Z or exact shape as Z, but with no values yet. So what I'm going to do is I'm going to use this function from the PyTorch library called empty-like. That's going to be here. And I'm just giving Z as an input. And this creates a copy tensor that is the exact same shape as Z, but no values in it yet. And now the two cases that I mentioned earlier, which is when Z is greater than or equal to 0, and when Z is less than 0, I want to clearly define them. I want to comment these sections so you sort of have an understanding of what part of the code belongs to which case. So in this case, I want to use this function, right? As it is given above and as we discussed just a minute ago. 1 plus exponent negative Z. Yeah, so this is the right function. And in this case, I want to use the version of the function that goes like this. Exponent Z plus exponent Z. Okay. So this part is clear, right? And I just want to point out that exponent, when I say exponent here, or as a function, this just means this, right? The e number to the power of whatever, and this exponent here happens to be the input that I'm giving to this exponent function. So yeah, this is basically exact same thing as this here, and same here. Okay. And the next thing that I'm gonna do is I will actually code it out. So I want to first of all clearly define a variable for this bit. So basically express this as a separate variable so we don't get confused. So I'm gonna just define exponent negative Z, and here's what I'm gonna do. I'm gonna say torch exponent negative Z, and then positive mask that we define above is indexed, and yeah, okay, so we're good. So now this code right here gives me basically this bit, right? We're within Z, we are only taking the values or the fields that are positive because we already defined them here. And then we are flipping the values of Z, so sort of we are just taking the negative of it, and then we are passing it on to exponent. And then, now that we have this variable clearly defined, we are gonna fill out the respective fields of our output tensor using the formula as such. So I'm gonna do a float here, 1.0 plus exponent negative Z. Okay, so I hope this is clear. That's it. So our output tensor in the fields where it's positive or Z is positive is now converted through this function, via this function. And now I'm going to do the same thing here, except here I don't need exponent negative Z, I just need exponent Z. So in a very similar way, I'm going to define a variable that's torch exponent Z. Here I'm using negative mask now. And okay, exponent Z is ready. So what I'm saying again here, take the bits or the fields of Z that are negative and pass them in into this exponent Z in this form, right? E to the power of whatever that value is. And then now I can fill the remaining fields of the output tensor using the right formula. And the formula here is expected exponent Z and divided by 1 plus exponent Z. So you can confirm that the function here matches exactly this function, right? So yeah, and then all we do is we return output tensor that we just redefined. So if I run this now, this block of code, my platform or the notebook that I'm using is going to remember all the implementation, updated implementation of this function. And later, when we will test, it will use the updated implementation of the student sigmoid function, and we will basically test if our function behaves as expected or it gives us correct results. So let's come back to this code block. Let's run this and let's test this. Okay, as we can see, the tests are passing now, which means our implementation was correct. Now we can move on to the next section, which is binary cross entropy loss. So you remember binary cross entropy loss from near end of our lecture on week 2, and you remember the loss function that we defined in this way. So for binary labels y, 0 or 1, right, and the predicted probabilities, which are shown with this symbol p, and which also happen to be the same thing as the sigmoid of z, the binary cross entropy loss is defined as such, and this is the loss function. In practice, we often pass logit z directly into numerically stable functions like BC with logit's loss, and that sort of saves us from all the manual work of having to define our own function and making sure it's stable and defining cases here like when z is greater than 0 or less than 0. So this basically does all of that for you, but here we want to be explicit, so that's why we are not using it. But in practice, usually say just using this function should be enough, and there will be parts of the basically code later that you will see where we just use this. But yeah, so so you remember this function, assuming that you remember this formula, we move on. We can implement binary cross entropy function. And the prompt is implement binary cross entropy, given probabilities P and labels Y, use a small epsilon or epsilons to avoid log 0. We will compare against PyTorch. So let me walk you through a little bit the inputs that we have here. We have probabilities, right? That's for P. We have targets, right? Or the labels. You remember they meant the same thing. That's denoted with Y, and then we have epsilons, right? And I'm gonna like sort of show you better. So you understand where probabilities and targets are already used, right? Like targets are here, probabilities are here. We're basically intending to use this formula, and to be able to use this formula, we need both inputs. So what we want to do here is we basically want to clamp the ranges of probabilities from 0 to 1 to some sort of range that is a little bit off by 0 and 1. So what I mean here, we do not want, in any case, the probability to be exact 0 or 1. Because what happens when we have a probability that's exactly 0 or 1? Let's say it's 0. If it's exactly 0, when we plug it in this formula, in this part of the formula, we get something like log 0. And log 0 is not properly defined. It gives us like infinity, negative infinity. So, and you remember from your calculus that log 0 is usually not a good practice. And if you have log 1, if you have a probability that's 1, this is log basically 1 minus 1, and this also turns into 0. So that's why we want to do something like this. We want to redefine this variable probabilities with this code. And what just happened here is that now we sort of shifted the values of the probabilities by an extremely small number. And if there was any 0 or 1 in the values of probabilities, now what happened is they're not 0 or 1 anymore. They're some values that are just slightly off from 0 or 1. And this is the very tiny value that I'm talking about. Okay, now that we have safer versions of our probabilities, we can actually apply the formula just like it is given here, and negative. So there isn't a huge negative, so I'm gonna just like close the bracket over here so we don't get confused. And inside the bracket, what I'm gonna do is I'm gonna say targets, right, which is our Y, times torch log. So I'm using the log function that's coming from the torch PyTorch library, and I'm gonna use the safe probabilities and another bracket here. So now we have 1 minus Y, and then this whole thing multiplied by torch log 1.0 minus props. Okay, so now we have a function that is the exact same as this one, and that's pretty much it. That's everything we need. So the next step is going to be just replacing this with return, and instead of returning loss itself, we're going to return mean of the loss. And this basically, what it does, it takes the average of all those individual losses and it gives us a single number. And this is important because optimizers like stochastic gradient descent expect one scalar value to minimize. Yeah, and basically loss.mean would turn a list of per sample losses into one overall average mistake, or not, in other words, just a single value the model tries to minimize during training. And we run this and we test. And you can see that our test is passing here too, meaning this function is correctly implemented. Okay. And the next section is going to be train, validation, and test split. So let's understand what train, validation, and test split was. Just a review of the last lecture. We split the dataset to estimate generalization and to tune hyperparameters without contaminating the test set. So train set was used to optimize the parameters like weights. Validation set was to choose hyperparameters and detect overfitting, and the test was final, sort of held out unbiased estimate set that we sort of kept until the very end, just to check the overall performance of our model once we feel confident in it. Yeah, so that is basically what it is. So what we're gonna do now is we're gonna generate the synthetic data set, and we will just run this code, and then I'm gonna also visualize that data set, and then I'm gonna just explain what I did. So we just created two Gaussian blobs that are roughly linearly separable. When I say synthetic data set, is you can see in this graph, right, x1 to x2 graph, that there are two classes of data, right? One shown with the color blue and the other shown with the color orange, that are spread across this graph, right? This area. And you can see that they are roughly separable, or they're roughly linearly separable, because there is very small overlap. So if you sort of draw a decision boundary right in here, you can somewhat separate these classes of data for the most part. Not perfectly, but for the most part. So this is what we did. This was completely random. Yeah, and yeah, so that's pretty much what we did here. And now we're going to be implementing train, validation, test split function, or in other words, a function that splits tensors x and y, x being our input vectors and y being our targets or labels that map to the respective inputs, into x training and y training, x validation and y validation, x test and y test, with the given ratios. So what's happening here is we start by taking the length of x and define it as n, and then the ratios that we are given, the deterministic split is 70% for the training, 15% for validation, 15% for the test. And if you remember from my lecture, this was one of the options using which we could split our data set, right? There was 80, 10, 10, there was 60, 20, 20, and there is also 70, 15, 15, which is also a popular split ratio. So what we do is we take this ratios input and we basically assign each of these individual numbers to certain variables, right? Ratio for training, ratio for validation, ratio for testing. And then we are just making sure that ratio for training, ratio for validation, ratio for testing, or these sum of these, basically amounts to 1, right? Basically just this, if this is amounts to 1 minus 1.0, this should be 0, okay? And this being 0 means it's smaller than this extremely small number, and this assertion should basically be true, right? So in other words, basically the translation of the statement is the ratios must sum to 1. And then what's going to happen is we're going to create and return a generator object that manages the state of algorithm, which in turn produces pseudo random numbers. And I'm talking about the function torch.generator here, this one. So that's what basically this function does. It's a function from the PyTorch library, and it basically returns a generator object that manages the state of the algorithm that produces random numbers. So you can look into that a little bit more in detail if you're curious about what it is. But yeah, basically using that, then we're gonna randomly permutate or reshuffle the numbers from 0 to n minus 1, right? Basically all the numbers in a consecutive way that our basically index or the length of our data set basically goes up to. Meaning if you have 1000 data sets, this would be 0 to 1000, except all the numbers are shuffled, right? That's what the indices or this variable is going to contain. And then the next thing that we need to do is we need to get the exact numbers to which these ratios corresponds to with respect to the length of our data set. So what I mean here is, let me give you a more practical example. So imagine we have 200 data points in our data set, right? That's the size of our data set. We already defined the ratios as 70%, 15%, and 15%, right? So if you had a data set of 100 data points, 70 of these data points would be for training set, and 15 of these data points out of 100 would be for validation, and the remaining 15 would be for test. But if we had 200 data points in our data set, instead of 70, we would have 140, right? Twice as many of those data points belonging into data to the training set, and 30 to the validation, and remaining 30 for the test, right? So this basically is what exactly this one is doing. This is getting the exact numbers like translated via the ratios that we use for training and validation and testing. And then we are basically this array of indices that we got that were shuffled and randomly permutated. We are gonna separate them for by basically these numbers, right? Meaning we're gonna, if again going off the example of 200 data points, because we had 70% going into the training set, 140 was now our index, the precise index for our data set that we wanted to allocate for the training set. So this basically takes all the indices of this array that also has indices as the values in them, and covers the span of 0 to 140 from it. And then this one does the same thing, right? 140 up to the next point, which is the number of training. So 140 plus 30, so 140 to 70. And then this one is basically from that 170 point up to the end of the data set, which was basically 200, right? So yeah, that's basically how we are separating these indices into training, validation, testing. And then finally, using these indices that we separated, right, for training, validation, and testing, we are getting the exact values of x and y tensors, or to be exact, x matrix and y vector, and we are splitting them, right, for training and validation and testing. And then finally, we just return these three pairs of, the matrix and the vector as a return statement. So that's the basically explanation for this function. And if we run, we can see that this passed as well, meaning this was correctly implemented. And now we are at the logistic regression. So we're going to go over the classes that we have defined the functions that we have defined within this class of logistic regression, and some external functions as well. And I'm going to walk you through what it is. So there's not going to be implementation here either, because these are pre-implemented. But yeah, it's important to understand what they do. Okay, so let's start with the prompt. So we use a single layer to produce logits, right? This is going to be the function that's going to give us activation input, or Z in other words. And we're going to just use the stable function that I introduced above, that basically combines sigmoid function, stable sigmoid function, and the next step. And accuracy the accuracy is going to use the threshold at 0.5. And so yeah, let's go. So the class logistic regression is going to have two methods. The first one is going to be basically an initializer. So what's happening here is we're basically initializing one linear layer, and that's going to map features to one logit. And the logit here means like unbounded real number. And forward here is gonna pass return forward pass returns logits, right? That's what's gonna do. And in general, the point of this class is basically to find a tiny neural net for logistic regression. And let's look at the accuracy from logits or accuracy helpers. So this basically this line here is going to convert logits to probabilities in 0 and 1. This line here, it is used to predict class 1 if probability is greater than or equal to 0.5, and otherwise the prediction is going to be just 0. And the return statement here is just going to share of the correct predictions between 0 and 1. And then we have the training function. And what the training function is doing is let's start in the first basically line. The first line here, building a model for our future count, and then this criterion here is basically a stable binary cross entropy that's gonna expect logits, right? Or in other words, it's just combining sigmoid and the binary loss, binary cross entropy loss, right? The function that I introduced earlier. And this is basically stochastic gradient descent. Weight decay here, meaning L2 regularization is 0.0 because that's what we passed in as an input. And then we are just introducing some lists that are gonna store our losses, for losses for training, losses for validation, and the accuracies for validation across the epochs. And we are gonna have 300 epochs. Okay, so let's look at the basically the for loop, the main for loop that we have in the function. This basically says, so we have 300 epochs. In each of these epochs, right, like 300 times, run this for loop, and at every epoch do this. Switch to the training mode of the model and forward pass on the training data, and then basically compute the training loss as a scalar, right? Remember this loss was scalar. And then there is a backward on training as well. So this one basically clears the grats, and then this one back propagates, and this one updates the weights. And here we are just tracking the train loss history, right? We are just appending or like adding the train loss that we got from this operation. And here we are switching to the evaluation mode. So with no grad tracking, what we are doing here in the evaluation mode, we are basically forwarding validation set. We are computing the validation costs here, and we are just computing the validation accuracy using this function here. And then these two values that we got from basically computing the validation loss and computing validation accuracy, we store them in the arrays or lists that we introduced. And at every 50 epoch, right? So if you have 300 epochs here, like at 0, 50, 100, 150, 200, 250, and 300, so basically 6 or 7 times, we are printing the values of losses and accuracies that we have, just to, basically print the progress. Yeah, and then we are returning basically the values, right? What the model was, what are the losses during the training across epochs, and what were the losses for validation, and what was the accuracies. And these basically is filling up all the, we are preparing the splits here using the train validation test split function we discussed earlier. This is training the logistic regression. And these are the values here, right? We don't have a regularizer. We have 300 epochs, and yeah, we are using the training, we're using the splits that we got from this function. And then we are printing out the result. So I'm excited to see what the results is going to be. So that's why I'm going to just run this cell. I'm just going to close this, by the way. Okay. Okay. So what we are basically seeing here is that the early training basically had a pretty big loss, right? You can see the loss here, and a very big loss for validation as well. And the validation accuracy was actually to 20%, which is like close to random, right? Very poor start. But by epoch 50, there's a huge sort of decrease in loss and increase in accuracy. It's pretty like sharp. So this means model learns, a good separating boundary very quickly, and the model improves significantly. And then across the other epochs, the validation just losses across both sets keep decreasing by marginal amounts, but they consistently decrease, and the validation just keeps increasing until we get the final validation accuracy at the end of our last epoch of basically 98%, which is a great number. And then we have a test training loop, and I want to test it as well, and yeah, we can see that they pass, which means the implementation was correct. Okay, and then what we are going to do here is we're going to visualize the decision boundary. So I want to run this first, and I'm going to talk about what this basic plot is, how to read it, and what everything on it means. So first of all, let's start with the background colors, right? This shows the model's predicted probability of class 1 at each location. The purple side is where we have low probability, where model thinks it's not class 1, or in other words, it's class 0. The yellow side is where there is a high probability that class 1 is located, meaning model thinks that side is class 1. And the smooth color change across the diagonal here, it basically is a sigmoid transition. And the dark contour line that you can see here, this is where the probability of class 1 is 0.5, meaning that's the decision boundary, right? And because we had a logistical regression with one linear layer, the boundary is straight line, right? And we have some faint parallel contour bands, right? So as the bands get tighter, that means the model's probability changes faster here. And yeah, and there are also some points that you can observe, right? The orange ones and the blue ones. So the blue dots mean those are the class 0, and the orange dots mean class 1. And most blue points lie on the purple side, and most orange points lie on the yellow side, the model, which means the model separates them well. And points very far from the boundary have high confidence, right? So like the ones that are deep purple, or like the deep yellow, bright yellow. And any points on the wrong side of the color basically would likely be misclassified. But we don't really seem to have many of them. What this tells is that the classes look roughly linearly separable. There's a linear decision boundary that fits them nicely, and the boundary runs diagonally, matching the way the two clusters are offset. And the visualization mostly agrees with our metrics, right? Because 98% validation accuracy, and the model draws a sensible boundary with small overlap between the classes. And what we're going to do here is let's talk about this section. There's also going to be a part where we will have to run the plots or run the chunk of code and have some visuals. So I'm going to run this. Okay, and yeah, we have two separate visuals here, and let's understand what they are. We are just training two models, one with regularization, one with no regularization, and the regularization that we use here is L2 regularizer. And we are just comparing the training validation losses and accuracies over epochs and decision boundary when we are basically plotting the decision boundaries for each model. And finally, we are comparing the weight norms to see how large the parameters grew. And you remember what underfitting, overfitting, and regularization was, right? Underfitting was when the model was too simple or not trained enough, with the high train loss or high validation loss. Overfitting was when the model fit the training specifics, including noise and outliers, pretty well or way too perfectly. And that's when we observe low train loss but reverse validation loss or accuracy. And yeah, you remember what the L2 regularizer was doing from the class. If not, I would prompt you to go back and review it. And we can see that the no regularizer validation accuracy is the same as the L2 validation accuracy here. But there are a difference in the weight norms. So weight norm no regularizer being greater than what L2 regularizer confirms the expected effect. We confirm that L2 regularizer indeed shrinks the weights as it should. But the reason why we are getting two validation accuracies between these two models that are exactly the same is because the data are roughly linearly separable even with the noise. And the straight line already does pretty well. So L2 doesn't change the shape of the boundary that much. It's still linear, and it mainly just tempers confidence and controls variance. On this data set and with the hyperparameters that we use, both solutions generalize similarly, but the L2 model is simpler because it has smaller weights, which is safer as complexity and noise would be increasing. The case when L2, like we can observe a better help or more usefulness from L2 is when we see a growing gap between train loss and validation loss. So when the train loss keeps decreasing and validation loss keeps increasing, that's a classic example of overfitting. Another case, it would be when we have higher dimensional features or even noisier labels, and when decision boundaries start reacting to the outliers more, meaning we make overconfident predictions. But yeah, so this is basically the comparison between two plots depicting decision boundaries and data using regularizer versus no regularizer. And we're going to do the final evaluation on the test set. And the final evaluation is pretty excellent. The test loss is at 10% and the test accuracy is over 96%. And with that, we can sort of confidently say that we trained the logistic regression model that performed pretty well. And that concludes the video for today. And we're looking forward to seeing you in the next weeks of MLF program. Thank you.